For the last topic in this set of videos, we'll look at some alternative substitution techniques. And there's going to be two. One is on the current slide, which is this higher roots idea, and then there's also a trigonometric substitution that involves using the tangent of theta over 2. So each of them are useful in a very specific context where they can really simplify an integral that otherwise looks very intractable. So this higher roots idea comes up if you have a factor of the form ax plus b, and then you take not just a square root but a higher ordered root, so an nth root, a cubic root or a quartic root or whatever. So this is also equal to ax plus b to the power 1 over n. And here what you're going to do is use the following substitution. You put ax plus b equal to a new variable u to the power n. So this u here is a new variable. Now if we take the differential of that, so we get on the left hand side a times dx, and then on the right hand side we differentiate with respect to u, n times u to the power n minus 1 du. So let's see that in action in an example. Let's take the integral from minus 1/3 to 2 of x dx cubic root of 3x plus 2. So we do our substitution. 3x plus 2 is equal to u to the power 3. And therefore 3 times dx is 3 times u squared du. And also we know from this expression that x itself is u to the third minus 2 divided by 3. So now we can write our integral as follows. We have that x here. So that becomes u to the third minus 2 divided by 3. We have dx. dx is u squared du. That's what dx gives us. And then finally we also have cubic root of 3x plus 3. So that's cubic root of u to the power 3. And so this term corresponds to this term right here. And now the remaining part is we have to fill in the boundaries of the integral because it's a definite integral. We know that if x is equal to minus 1/3, then from the formula you have that 3 times x plus 2 is minus 1, it's plus 1. So u to the third is plus 1, and therefore u is also plus 1. And likewise, if x is 2, then you get 6 plus 2 is 8, so u cubed is 8, and u itself is 2. And so we add that to our integral, we integrate from 1 to 2. And now we have a integral that has a rational function for the argument. So we have integral 1 to 2, and let's simplify that a little bit. So we know that cube root of u cubed, that's just u, and then we have a u squared in the denominator, in the numerator, sorry, so that becomes a u. So we are left with 1/3 u to the power 3 minus 2 times u du. And we can integrate that to give us u to the power 5 divided by 5 minus 2 times u squared divided by 2. And we have to evaluate that at the bounds 1 and 2. And now it's just a little bit of simple algebra. So we will get 1/15 for the first term, 32 minus 1, minus 1/3 for the second term, 4 minus 1. And now if you simplify that, we get 31/15 minus 1. And that finally gives us 16/15. So this is a useful rule to employ when you have higher powers in your integrand somewhere. And it doesn't have to be exactly of the form that I just sketched. Sometimes it can be a bit more general or a bit more specific. So let's look at another example where now we have the integral of dx over x to the 1/2, so square root x, 1 plus x to the power 1/3. And that looks like a forbidding integral, but let's see if we can do something. So let's write this out as 1/2, and then x to the power 1/2 plus 1/3. That's the product rule here for the powers. And so we know that this will then become x to the power 5/6. So let's write that down one more time. 1/2 plus x to the power 5/6. So this x to the power 5/6, that's really the thing that scares me the most at this point in time. So let's see if we can eliminate that somehow. And we're going to use our rule of higher roots substitution. So we want to eliminate this term in particular. And in order to do that, we'll use substitution, or we'll try a substitution. X to the power 1/6 is equal to u. So that square root of x, I don't worry so much about. Probably I'm going to be able to do something with that, but that sixth root, that really gives me a headache, so let's try to get rid of that. So if we make this substitution, then the differential becomes 1/6, or actually let me rewrite it a bit. So this is equivalent to saying that u to the power 6 is equal to x, and therefore dx is 6 times u to the power 5 du. And so now with that substitution, I can rewrite my integral, 6u to the power 5 du. And now I need to do something about that x to the power 1/2. But I already know something about x to the power 1/6. So from this I can also derive that x to the power 1/2. That is x to the power 1/6 to the third. So that is u to the power 3. So now we substitute u to the power 3 for x to the power 1/2. And then 5/6, that's plus u to the power 5. So just let's put the colors on it to see where things come from. So the yellow term becomes u to the 5. The blue term, that's x squared, 1/2, sorry, and then the red term, that's the differential. All right, so now let's take out the 6, and we can split off a u squared, or sorry, u to the third from each side, and write this as u squared du u squared plus 1. Now you might solve this with the partial fraction expansion. That would give you very correct answer. I'm not going to do that. I'll take a small shortcut. So if I have my integral like this, what I can do is I can write plus 1 minus 1 here, and then my integral becomes 6 times integral of u squared plus 1 u squared plus 1 du minus 6 times integral of du u squared plus 1. And of course, u squared plus 1 over u squared plus 1 cancels, and I have 6 times u for the first term, and then minus 6 times the inverse tangent of u plus a constant. And last, back substituting, I get 6 times x to the power 1/6 minus 6 times tan inverse x to the power 1/6 plus my constant. And then last, one further substitution technique, which is known as tan theta over 2 substitution. So this is useful if your integrand is a rational function of sine theta and cosine theta. So in that case, what we're going to do is we're going to make the substitution x equal to tan theta over 2. And so in other words, theta here, or new variable, is inverse tan of 2 times x. And therefore d theta is 2 times dx 1 plus x squared. And now, given x equal to tan theta over 2, there's 2 trigonometric formulas that we can derive from that. So from this we can derive that cosine theta is equal to 1 minus x squared divided by 1 plus x squared, and sine theta is 2 times x 1 plus x squared. That's just using the half angle formulas. I will let you check this by yourself if you don't remember how these formulas come about. So please check this just to make sure that you know where these formulas come from. And these formulas are also why we care about this substitution in the first place. You can see if you have something as a complicated function of cosine and sine, what you can do is you can substitute something that's a rational function in x, and hopefully you then get a simpler integral. So let's see how this works on an example. Let's take d theta 2 plus cosine theta. So this is not necessarily an integral of the form that we've seen before, but we can use our toolbox. So we make the substitution x equal to tan theta over 2. And then we know that d theta becomes 2 times dx 1 plus x squared. So I'll write that here. So that's our differential. And then the integrand itself, well, it's 1 over 2 plus, and then cosine theta. And for that, I'm going to have to use my formulas that I derived. And write this as 1 minus x squared, 1 plus x squared. And now you can see, now I have a nice rational function in terms of x. And I can use my partial fraction expansion. So if I put everything on the same denominator and I simplify the 1 plus x squared, I get 2 times dx, 3 plus x squared. This is one of the cases that I've seen before, or I can link this to the inverse tangent. I may have to do a few substitutions to get rid of the 3, but ultimately what you get here is 2 times 2 divided by square root of 3, the tangent inverse of x divided by square root of 3 plus a constant. And now we still have to write this in function of theta, so we substitute our expression and we get 2 over square root of 3 inverse tangent of 1 over square root 3 tangent of theta over 2 plus a constant. And this is my final answer. I don't know of a way to simplify the inverse tangent and the tangent into something less involved, so we leave it at that.